Okay, concavity and points of inflection. In this lesson, I'm going to go through one example here, hopefully under 10 minutes, and I'm going to break it down. Here's an example for the function y equal to x to the fourth minus 4x cubed. Find points of inflection and local extrema, then I sketch the graph. All right, we're going to go ahead. We're going to do the first and second derivative right away, and then we're going to analyze what is happening between critical points and possible inflection points if it does have it. So let's go ahead and do the first derivative and second derivative. Now that we have that, let's find the critical points by setting the first derivative equal to 0 and then solve, and you will get x equal to 0 or x equal to 3. Those are the x value of the critical points, and we can go ahead and use the second derivative test to see what is happening at the critical points. So let's do that. So we're going to plug it back in there. So f double prime of 0, that's equal to 0. And then f double prime of 3, that is equal to 36, which is greater than 0. Okay, now we're going to go ahead and analyze. So for the first, for the positive 3, we know that f prime of 3, that's equal to 0. We already showed that. And we know, based on the double derivative, f double prime of 3 is greater than 0, which is right here, okay, 36. And f of 3, if you plug it back into the function, you get negative 27, and that will give us the local minimum. Okay, so that's the first kind of a test. We can find the local minimum. Now, with x equal to 0 to f double prime of 0, which is equal to 0, this test is inconclusive. That means we have to go back to the first derivative, and it seems that if you test the values, the interval that are less than 0, and between 0 and 3, you notice that f prime, the first derivative, is less than 0 for these values that are less than 0 and between 0 and 3. And that tells us, what does that tell us? Well, that tells us that at 0, at x equal to 0, there is no local extrema. So we don't have neither minimum nor maximum value there. Okay, now we're going to go ahead and find possible inflection points because we don't know that yet. We have to set f double prime, the second derivative, equal to 0 and go ahead and find inflection point. So let's do that. And to find possible inflection points, we just take the second derivative, which is up here, 12x squared minus 24x, and we factor it and set it equal to 0. And let me set that equal to 0, and then solve, and we get two possible values for inflection points. We don't know if it is or not, but we have to check. So x equal to 0 and x equal to 2. And then we're going to go ahead and because we have to do a test interval between these two values to see if the graph, the value of this f double prime changes a sign. Okay, let's do the table. So here is a table there, and these are the intervals. So we're going to go look at the values that we found by setting the second derivative equal to 0. We're going to go to the left of the first value, which is x equal to 0, so negative infinity to 0. Then in between the two values, and then anything greater than 2 to see if there is a concavity change, in curvature in terms of the sign. And this is the second derivative sign, and let's see what happens. If you're plugging a negative value in here, you notice that negative in here times a negative will be positive. So when you have any interval between negative infinity to 0, that's positive. So this is upward, okay? And then between 0 and 2, you plug in there, let's say 1, and you notice that it's a negative value, so it would be negative. That is going to be downward. And then the last interval will be positive because the values both are positive, and this would be upward again. Okay, And so what does that mean? That means that we have 0, 0 is the point of inflection because it changes direction. Notice the between negative infinity and 0 and 0 and 2, we change the sign and sign again, right? So we know that, so that implies that now we got ourselves 0, 0 is the point of inflection. And also we have 2, and when you plug it back into the equation, you get negative 16 is point of inflection. So these two, we have 2 points of inflection because they changes the sign. That's great. Now we can go ahead and look at the concavity and look at the curvature change. And now that we have all this information with the critical points, we can go ahead and sketch the graph. So let's go ahead and sketch the graph. And here is the graph using the critical points 0, 0, 3, negative 27. It's kind of roughly sketched. Obviously, it's not 100% accurate because we don't know the x-intercepts, but in terms of the curvature change and inflection points and critical points, we can see that we have a local, well, in this case will be a absolute minimum at negative 27 for this graph, but we do not have any other extreme out there because at 0, 0 the curvature changes, but it's inconclusive in terms of having any kind of extrema. And then of course we have at 2, negative 16, that's another inflection points with 0, 0. Notice that 0, 0 is a critical point and an inflection point, and that can happen. Yes, it can happen. And then 2, negative 16 as well. So notice that the curvature changes at 0, 0. Then at 2, negative 16, we did a test value with the double derivative, the second derivative. We notice that it changed again to the upward, which is concave up. And then we have a cup y, concave up, which is like a cup, and it changes the direction. And because it changes direction, that's another inflection point. And here is your final answer to this question, where we analyzed the function using the inflection points and finding the extrema and the critical values. All right, hope all is well. Until next time, check out the next video in this series.